In this experiment, I will try to explain how to use or develop models to describe simple physical behaviors by using the tracker software. What's the model? There are many meanings of model in real life, but we are concerning the models in physics, so I will try to give you the essence of the meaning of models in physics in the perspective of the motion in one dimension. How we develop models to describe the motion in one dimension? So far, we have seen some physical quantities relative to the motion, which is position, distance, velocity, speed, acceleration. All these physical quantities are subject of the kinematics. In kinematics, we only deal with the trajectories of systems or objects. We don't care about their masses or internal properties. So far, we have seen some simple models in motion. Simple models of motion may be the particle stay at rest forever. If you choose a reference point, when you observe that the object or system does not change its position, so its position is not a function of time, then you say that the particle at rest. Or you observe that the object moves in this fashion. In equal times, if it changes its position in equal amounts, then we say that it's a constant velocity motion. It's a model. The constant velocity model is the model that the object or system changes its position regularly equal amounts in equal time intervals. But you may sometimes observe that the object changes its position like this. It increases its position every time duration. If this increase is again regular, then you say that the object is accelerating with a constant acceleration. This is another model. This is the model of the constant acceleration motion. We can describe models just using the definition of the physical quantities, or we can describe these models mathematically. The mathematical description of these models are like x of t is x0 for the first one. The position does not change, the particle is at rest. For constant velocity, the mathematical expression is just initial position plus some constant velocity multiplied by t. This is the mathematical model for the constant velocity motion. And for constant acceleration motion, this is the model. So you can either describe the models by word in a very rigorous way using the rigorous definitions of physical quantities, or in a simple way you can describe these models mathematically. Mathematical models are just analytical functions of time. So this is the concept of model in physics. Now I will try to give you two ways of reaching some models by using scientific steps. The first one is the model making. What is the model making? How we make models using model making method? If there is a problem of defining the type of motion of a particular object, this is your problem. And what you do is you observe the motion firstly and develop some hypothesis. The hypothesis about this motion depend on just your observations. These observations may be heuristic observations. You might just sense that the motion looks like a constant velocity motion. So anyway, you just have an idea. This is hypothesis, and hypothesis sometimes can be also referred as a model. There is a model in your mind. Let's say this is a constant velocity motion. But how do you verify? To verify this, what you have to do is you have to get some real data from this observation. You have to make some physical measurements, rigorous measurements by using rigorous instruments. Upon data, you analyze the data and as a result of this analysis, make some parametric estimation. Since you have already developed your model in your mind, try to estimate some parameters in your model so that you try to fit this model into your data. If this fits, I mean, if your model explains where the object will be successively at a later time, then your model is successful and you're done. But there might be cases that even there is a model in your mind with some parameters, when you analyze the model, it may successfully define the real motion just for a limited time. But after some certain time, the model is not able to predict the real motion successfully. It diverges from the real data. In that case, you'll see that you have to modify your model because even though for a few data it fits to real motion, you observe that there is some kind of divergence from the real observation in your model. So your model is not successful for all of the range of motion. So then go back, try to make a new model. You might see that the motion looks like a constant velocity motion, but just for a few data, constant velocity model fits your real observation, but after like 4 or 5 data points, maybe at 6 and forthcoming data is not fitting to your model. Then you will think that I changed my model so that there might be some kind of very small acceleration. So make model that the new model is not anymore the constant velocity model. You just make a model of constant acceleration and find your parameter or estimate your parameter of constant acceleration. And observe that this new model fits to your real motion for a given range and fits in the range of error analysis. Of course, there is going to be some errors. I mean, your model will not estimate 100% true position time values for the motion. There is always going to be some kind of error, but if this error is not going to increase and for every data point, these error values are just within the range of measuring errors, then your model is successful. You have to make error analysis and you say that within these experimental measurement errors, the model fits to real data. Then you are done. So it's kind of a circle. You're just developing a circle until you reach a successful model within the range of error. This is one way. The second way is you directly get your data and make analysis of data. Upon analysis of data, try to visualize this data with some plots. An example that put your data in the perspective of one-dimensional motion, make the plot of your position. In this example, our data is position and time. For every time, what is position of the object? Suppose this is your data. When you look at data in the plot, this doesn't look like a straight line. It looks like maybe a parabola. Why do you think so? Because in your mind, you are just doing some kind of fitting to these data points. Sometimes the points might be just off this hypothetical line. In your mind, what you are doing is just, this is not a straight line and it looks like a curve. And there is a known mathematical model or fitting for this kind of curves. I might choose the parabola. If not, if your data looks like this, you choose line. If your data going up and down, it might be a trigonometric. So there is a set of mathematical expressions and analytical functions. And what you do is just try to fit your data to this set of non-analytical functions upon data analysis. So you are not developing a new model, you are just choosing some mathematical functions, non-models to your data, so that your data fits to parabola, line, etc. For example, parabola has this general expression. Let's say at squared vt plus c. Well, it looks like a parabola, but how do you fit the parabola to your data? You have to determine these parameters, but usually computer software are doing this because computer software are very efficient in this type of jobs. So you just enter these data, we will do it in tracker and go analysis and ask tracker to fit a mathematical function. Let's say ask tracker fit a parabola to my data, and what the tracker does is it determines these ABC constants as best as possible. So once you determine these ABCs, then you are done. And how do you know that you are done? Again, what the tracker does after determining these parameters, it also gives you some error analysis in terms of root mean squared. It will give you some error number, saying that I've chosen these parameters, but these parameters fits to real data within the range of this error value. If this error value that the tracker has found through analysis is within the range of measurement errors, then you are done. If this error value is within the range of measurement errors. How do you know about the measurement errors? I will explain this in tracker. When we analyze a real video of a real experiment, and I will explain you how do you get data out of the video of a real experiment. The experiment will be about the motion of an object. It's going to go frame by frame because every video has some finite numbers of frames. For each frame, you will get these position and time measurements. I will show you how to do it, and you will know your error in the position measurements. These error values will sum average, and when you compare this error analysis done by the tracker, if they are the same within some range values, I mean, if this error and the measurement error are comparable to each other, then you say you are done. The method using the known model defined through data analysis has the name model breaking because you are breaking known models by using data analysis and also error analysis. So in the second method, you are doing model breaking. In the first method, you are doing model making. So this is the difference. We'll go both ways in some cases, so you will know how to get the successful results of any of these two models. So let's come to this again. So once you are okay with this error analysis through the determination of these parameters, and the errors from your measurements are comparable to each other, then you say that this is the model, but if they are not comparable to each other, if this error RMS is larger than the measurement errors, then this cannot be a successful model. You will see that if the motion continues, this model will not predict the real motion successfully. It will diverge. So what you do then? You had chosen the parabola. Then there might be a cubical expression like ATQ plus BT squared plus CT plus D. You might have this expression as a model. So you choose another known analytical function and go through the same steps. Make tracker determine the parameters and also determine the root mean square analysis, which is the error analysis. If it's comparable to your measurement errors, then you are done. If not, continue to circle, just like in the case of the first method. So, these are two approaches making models in physics. In fact, if you look at these carefully, what you are doing on these two methods is you are just following scientific steps. These are nothing but applying the scientific methods to describe a physical phenomena or physical case. It's good thing that we have a tool, the tracker, which allows us to use models in our course through these methods. In this experiment, I will try to show how you use models through these methods for motion in one dimension by using tracker.